My name is Bill Smith. I'm from NASA Langley, and I'm going to talk about some new ways that we're using satellite data and fusing it with other remote sensing data to detect severe storms. And this is not something that I work on.
We can't hear you very well. Maybe
but
try to
work done by my colleague Chris Bedka, and this is in collaboration with University of Alabama in Huntsville and University of Oklahoma. So Chris couldn't be here, unfortunately, but this is a 1-minute animation of multi-sensor observations of severe storms. This is from one day last spring. And so in the upper left, we have a visible image from GO-16. The infrared is in the upper right. In the lower left, we have weather radar data. And in the lower right, lightning flash data. This is from a ground-based network, but it's analogous to what we would get from GO-16. So on this day, there was something like 125 severe weather reports of tornadoes, wind, and hail. And all this information, of course, is available in weather forecast offices, but it can be difficult to assess quickly and difficult to determine exactly when and where these severe weather is going to occur. So what Bedka's team has done is developed a method to fuse all this information together into one product with the goal of simplifying the assessment in weather forecast offices, but also to improve the accuracy of determining when and where severe weather will occur in the next hour, and also for distinguishing tornadic from non-tornadic severe storms.
Use that one.
Okay. Okay, I think our collars are getting in the way of that mic. So that's the goal of the project. Now, this is a depiction of the various elements of a severe thunderstorm. Of course, we have strong updrafts, frequent lightning, storm rotation, and rapid outflow aloft. And the radar data provide a good depiction of the storm structure and air motions and rotation. From satellite now, we have a geostationary lightning mapper on GO-16, so we can detect where lightning is occurring frequently. And we can also detect patterns in the cloud images that indicate where overshooting tops are. And that's overshooting tops, of course, are associated with the strongest convection, where the clouds are penetrating up into the warmer stratosphere. And also associated with the overshooting tops are these above anvil cirrus plumes in the stratosphere. So in developing this data fusion approach, a lot of data goes into it. They've looked at 10,000 storms that occurred during 34 different severe weather outbreaks, and basically compiled statistics of various parameters from these different data sets, and sorted them according to whether the storms were tornadic or not tornadic. And basically, when tornadoes are on the ground, the remote sensing data shows that the parent thunderstorm has the strongest updraft, produces the most frequent lightning, ejects cirrus outflow the fastest, and rotates the fastest. So what this depiction on the left sort of shows is that they have good sensitivity in these different parameters for separating non-tornadic storms from tornadic storms, and even for providing some lead time to when tornadoes touch down. And in fact, when they validate this method and compare it to standard methods being used in National Weather Service offices, they find that they can get about a 30% improvement in the detection of tornadic storms, and also in advanced warning time. So finally, this animation highlights this above anvil cirrus plume. And that's the strongest indicator of a severe storm in visible and infrared satellite imagery that they found. And so you can see the above anvil cirrus plume there in white. And I'll animate it one more time. But basically, these are generated by intense updrafts and gravity waves that inject the ice crystals into the stratosphere. And because they're in the stratosphere, they appear warmer than the underlying anvils. And they're textured and cast shadows, and so they're fairly easy to detect. The plumes producing storms generate about 17 times more severe weather per storm than those without the plumes, and they're associated with about 80% of the most severe weather that's reported. That's the highest winds, large hail, and the stronger tornadoes. And on average, these plumes appear about 14 minutes before severe weather is produced by the parent storm. So that's it in a nutshell. This is one way that we're using satellite data and fusing it with other remote sensing data to improve severe weather forecasts. Thank you.